So in the last video, I explained the definition of a sequence and also boundedness of a sequence. When you say that sequence is bounded, how to define a sequence? Sequence is, it is a function from set of naturals to reals. Set of naturals to reals. Usually a sequence means we denote the sequence by its nth term. Definition means it is a function from natural numbers to reals. But how we denote a sequence? Sequence is denoted by its nth term or by writing the range of the function. We denote the sequence. I have already explained by taking example. Say suppose un is, it is a sequence denoted by this notation, or sequence is also denoted by Sn or An and so on. Suppose un is a sequence defined by un is n by n plus 1. Then we denote the sequence only by un is n by n plus 1, or by writing the images. Same sequence can be denoted by this. What is n here? N is any natural number. So it is, take n is 1. Natural number starts from 1. 1 by 2, 2 by 3. N is 2, 3 by 4, 4 by 5, so on. Always sequence means we consider infinite sequence only. This is the definition. Next thing is, when do you say that sequence is bounded? When do you say that sequence is bounded? A sequence is bounded if un mod un less than or equal to k for all n. That means there exists number k so that un is greater than or equal to minus k, less than or equal to k. Then we say that sequence un is bounded. I explained only these two things in the last period, and also I explained definition of convergence of a sequence. That is important. When we say that sequence is convergent and divergent. Convergent means a sequence un is said to be convergent if for epsilon greater than 0 there exists m, a positive integer, so that mod un minus l is less than epsilon for all n greater than or equal to m. I repeat this definition. A sequence un is said to converge to L. L is called limit of the sequence. If for all epsilon greater than 0, for all epsilon greater than 0, that is important, it is arbitrary, there exists a positive integer m, so that un minus L is less than epsilon for all n greater than or equal to m. What is the meaning of this? So of course, always definition means it should be very precise. You have to remember definition as it is, because definition may be asked. When do you say that sequence is convergent? Then you have to write precisely this definition. But what is the meaning of that definition? If you only by heart the definition, that is not sufficient. You have to understand the meaning. What is the definition of convergence of a sequence? Say a sequence un is said to converge to L means, for infinite sequence means it consists of infinite number of terms, and un converges to L means the infinite number of terms of the sequence lies between or lies in this interval. It is however small interval. Infinitely many terms. That means there exists m, large positive integer, for all the values of this un, for all n greater than or equal to m means, therefore all the terms n greater than or equal to m means n1, n2, n3, etc. There you will get correspondingly terms of the sequence. All that terms of the sequence lies in this small interval. Then we say that sequence converges to L. That is the meaning of convergence of a sequence. Now, one important thing here. This is helpful to prove that sequence is not convergent. Suppose we have to prove that sequence is not convergent. Then we use this. What is that? If a sequence xn, see I use different notations here, xn, un, an, etc. If a sequence xn convert to L. Convert to L. Then for epsilon greater than 0, there exists a natural number P. For epsilon greater than 0, there exists natural number P such that mod xn minus xm is less than epsilon for all nm greater than or equal to P. Important thing it is. This is the definition of convergence of a sequence. Now using that, when the sequence converges, xn converges to L, then, or when a sequence converges may not be to L. When a sequence xn converges, then for epsilon greater than 0, there exists a natural number P, fixed number, so that mod xn minus xm is less than epsilon for all nm greater than or equal to P. What is the meaning of this? Say suppose xn converges, then what happens? For there exists fixed positive integer, so that n and m are greater than or equal to P. They are however large. Suppose n is 1000. For the sake of definiteness, may not be equal to 1000 always. Suppose n is 1000, m is 2000, or n is 2000, m is 1000. Then xn minus xm means the difference between 2000 term and 1000 term of the sequence must be less than epsilon. N and m are arbitrary, not only 2000 and 1000. Any large term of that sequence, difference between that two terms must be less than epsilon. If a sequence converges, then mod xn minus xm less than epsilon for all nm greater than or equal to P. Important result, we use this to prove that some sequence is not convergent. How to prove this one? To prove this, since xn converges, since sequence xn converges, let xn converges to L. Sequence xn convert to L. What does this implies? This implies mod xn minus L is less than epsilon by 2 for all n greater than or equal to P. See the definition of convergent sequence. When do you say that un converges to L? For epsilon greater than 0, there exists a natural number m, so that un minus L is less than epsilon for all n greater than or equal to m. Now instead of m, we have taken P here, and epsilon is replaced by epsilon by 2 because it is arbitrary. Since xn converges to L, this implies mod xn minus L is less than epsilon by 2 for all n greater than or equal to P. There exists this P. Suppose n and m are greater than or equal to P. Then what happens? Mod xn minus L is less than epsilon by 2. xm minus L is less than epsilon by 2. Correct? Epsilon by 2. M and n are greater than or equal to P, then we have these two. Now consider mod xn minus xm. It is equal to mod of xn minus L minus of xm minus L. Correct? Say I have written xn minus xm as xn minus xm minus L plus L. Now it is less than or equal to mod of xn minus L plus xm minus L. So it is less than epsilon by 2 plus epsilon by 2. So it is epsilon. So it is important result. When if a sequence xn converges to L, or if a sequence xn converges, then there exists a natural number p, so that mod xn minus xm is less than epsilon for all nm greater than or equal to p. There exists a fixed integer, so that if you take however large numbers greater than that p, the difference between the terms must be less than epsilon. I think the proof is clear to you, and this is very, very important result. Now we consider one theorem here. Theorem is, if a sequence xn converges, then it converges to unique limit. A sequence xn, if a sequence xn converges to L, then L is called limit of the sequence. The limit of a sequence is unique. Result important. Suppose a sequence xn converges, then it converges to unique limit. To prove this, we prove by contradiction. We prove this result by contradiction. Result important. Contradiction means we suppose that sequence converges to two different limits, and we prove that two different limits, say L and L dash, then we will get some contradiction. So it is not possible. So the limit is unique. So the proof is like this. Let the sequence xn convert to L and L dash, where L is not equal to L dash. We start with this. Suppose the sequence converges to two different limits, L and L dash, so that L and L dash are not equal. Therefore L minus L dash is not equal to 0, and mod L minus L dash is greater than 0. Correct? Say, we suppose that sequence xn converges to two limits, L and L dash, they are different. Therefore L minus L dash is not equal to 0, and mod L minus L dash is greater than 0. Now we choose epsilon is equal to half into mod L minus L dash. This is important step. Take epsilon is equal to half into L minus L dash. Now what we have taken? Xn converges to L. When do you say that Xn converges to L? Since Xn converges to L, for epsilon greater than 0, there exists m1 positive integer, such that mod xn minus L less than epsilon by Sn minus L is less than epsilon for all n greater than or equal to m1. Again, say you may use any notation here. In place of xn, Sn may be used, or an, yn, different notation may be used. So usually xn and Sn are used. Say I have taken xn sequence here, it converges to L and L dash. Since it converges to L, we have this. Also, since it converges to L dash, we have mod xn minus L is less than epsilon for all n greater than or equal to m2. There exists m2 natural number, however large, so that mod xn minus L is less than epsilon for all n greater than or equal to m2. Now we choose m is maximum of m1 and m2. Maximum of m1 and m2. Then what happens? Then from these two, mod xn minus L is less than epsilon by 2 epsilon. Mod xn minus L dash here, L dash is less than epsilon for all n greater than or equal to m. By choosing m as maximum of these two, m1 and m2. Now consider L minus L dash or mod L minus L dash. I take mod L minus L dash. Mod L minus L dash can be written as mod xn minus L dash plus or minus of xn minus L. Say, am I correct? This L minus L dash is written as xn minus L dash minus of xn minus L, because by rearranging this term we get this. It is less than or equal to mod xn minus L dash plus mod xn minus L. Mod xn minus L. Now what is xn minus L and xn minus L dash? They are less than epsilon plus epsilon. It is equal to 2 epsilon for all n greater than or equal to m. Say mod L minus L dash is equal to 2 epsilon. But we have, what is mod L minus L dash? Mod L minus 2 epsilon is mod L minus L dash. Using this, what do you get? Using this we get, it is equal to mod L minus L dash. I think you followed this one. Mod L minus L dash is less than mod L minus L dash. If we suppose that this xn converges to two different limits L and L dash, then we will get mod L minus L dash is less than mod L minus L dash. It is absurd, which is not true. Therefore, our assumption is wrong. This xn doesn't converge to, or any sequence doesn't converge to two different limits. If it converges, then it converges to unique limit. I think you have followed the proof of this. You go through the video once again. Have any difficulties, you can ask. Now, next result is every convergent sequence is bounded. Every convergent sequence is bounded. In the last video I explained when we say that sequence is bounded. What do you mean by sequence is bounded? A sequence UN, say I may use different notations, UN, SN or XN. Because different authors use different notations. In the examination you may get sequence as SN, XN, UN or even AN also. So I use all these notations. Now, when do you say that sequence is bounded? A sequence UN is said to be bounded if mod UN is less than or equal to K for all n. Then we say that sequence UN is bounded. Now, every convergent sequence is bounded. Now I suppose that sequence XN or SN is convergent and prove that it is bounded. To prove that it is bounded, we have to prove this. Now we use definition of convergence only. Proof is, let the sequence SN be convergent. And it converges to L. Then what happens by definition? For epsilon greater than 0, there exists M belongs to N such that mod Sn minus L is less than epsilon for all n greater than or equal to M. This step is quite straightforward. I think there is no difficulty in understanding this one. What we are proving now? Every convergent sequence is bounded. Suppose Sn is a sequence which is converges to L. Then by definition of convergence, mod Sn minus L is less than epsilon for all n greater than or equal to M. Epsilon is arbitrary here. Take epsilon is equal to 1. take epsilon is 1. Then what happens? Mod Sn minus L is less than 1 for all n greater than or equal to M. Now what does this implies? This implies you have studied inequality of absolute values. This implies L minus 1 is less than Sn less than L plus 1 for all n greater than or equal to M. What you have to prove? You have to prove that the sequence is bounded. And also you know that to prove that sequence is bounded, you have to prove that mod Sn is less than k. Now we take small k is minimum of S1, S2, etc. Sn minus 1 and L minus 1. L minus 1. And capital K is maximum of S1, S2, etc. L plus 1. L plus 1. For all n greater than or equal to M, we have this. Sn is greater than L minus 1, less than L plus 1. But we take K is minimum of all this, S1, S2, etc., Sn minus 1 and also L minus 1. L minus 1. And capital K is maximum of this S1, S2, etc., L plus 1. S1, S2, etc., L plus 1. Then what happens? Then small k is less than or equal to Sn, less than or equal to k for all n. For all n. Because we have chosen small k is minimum of this S1, S2, etc. So Sn is greater than or equal to k. And we have chosen capital K as maximum of S1, S2, etc. So Sn is less than or equal to k for all n. What does this imply? This implies sequence Sn is bounded. Sequence Sn is bounded. But the converse of this is not true. Important. What is the converse of this? Every bounded sequence need not be convergent. What is the result? If a sequence converges, then it is bounded. But converse is not true. Every convergent sequence may not be, every bounded sequence may not be convergent. I explain by taking this as an example. Can I take this in next period, because this video we can do up to 20 to 25 minutes. Okay, then I continue that converse is not true in the next video.